Welcome to micro communication course. Today we see a slot line. So we have seen earlier a microstrip line. On a microstrip line, there is a small strip on the substrate, and then below the substrate there will be a uh, conducting plate, that is the ground plate. Then we have seen that a coplanar line. In a coplanar line on a substrate, that three metal conducting layers are there, or three conducting lines are there, and in between that this two line, that is central conducting line, that will be your main line, and other two will be a ground line. So now another type of a line here, it is about slot a slot line. It is just like a planar transmission line or a planar transmission structure. Now how that slot line configure here? Okay, so now we have seen earlier that is strip line. Now similar kind of structure is there for the slot line. Okay, so in this we have a substrate there. When we say that this one is about a substrate here. Now, and this one is about nothing but a slot. So this particular case here, if you see, okay, now this one is about a slot line. So this one is about a conducting patch we have. Okay, this one we see here. Okay, if you see here, this one we have conducting patch. This one is about a conducting patch here. So if you consider the diagram, so it will look like this one is slot. So this one is a width here, small separation between these two conducting plane. Okay, and here we have a small gap between these two conducting plate. Okay, these are nothing but a conductive plate, one conductive plate, another is a but conductive plate, and these conducting plates are placed on the substrate. This one is a substrate. Okay, and for the given substrate, it has some epsilon r value as per the type of material we are using, and what will be the height of the substrate. Consider that height, as well as for this conducting plane it has some particular thickness. Okay, this one, so this one is about a thickness t here. Okay, so this one we say that a thickness t, right? And this one is about a height of the substrate. On this particular substrate, these are the two conducting plane are there. Now if you see that we have a dielectric substrate there. On one side of the dielectric substrate, these are the two conducting coating or a conducting wires are there. Okay, this one is about a conducting, and that conducting wire or a conducting strips, it has a thickness T, and the separation between these two conducting strips is a W here. That's why this particular section, okay, separating this particular section, it will be act as a slot here. So that's why this particular line is called as a slot line. So in between these two conducting planes, there is a slot section. So that's why it is called as a slot line. So now we can consider that a field distribution here. So what about the field distributions in this particular line? So in that case, if you see the given line, a slot line here. So now for the electric field component, it is the easiest to understand that what will be the field distribution. But for the magnetic field here component or for magnetic field line, that is difficult because these are the two different conducting wires. Okay, so for the two different conducting wire, that magnetic lines will be different. For the electric field, it's just like easy one. So which one is a positive and another is to be considered as a negative one. Which one is a positive and another is to be considered Okay, we can say that this one is active and this one is considered as a ground now. So in that particular case, if you see the electric field lines across this, so how it will be? So your electric field will be likewise. Okay, these are nothing but the electric field lines. So on this particular plot. But in the case of a magnetic field, if you see the distributions here, okay, see simple distributions here, likewise. We can say that there will be a simple distribution. Even from the substrate itself also. Okay, so likewise, okay, from the substrate also. So this way we can say. So we can say that this one is about the electric field line distribution. But in the case of a magnetic field line distribution, so it will be difficult because around this wire, around this particular conductor, there will be a field. So in that case, the field will be likewise. We can say that we have the magnetic field around this particular wire. Okay, so we can say that this one is about a magnetic field around the wire, and so that in that particular case, we just supposed to be draw this a field distribution. So likewise, we have a field distributions. Likewise, we say that direction of a field here. Likewise, magnetic field is likewise here. So similarly, for this particular section, the direction will be different. So I supposed to consider that here we have okay. So the patch will be what? You can say that this one will be the a magnetic field line distribution. Okay, so this one. So if supposed to be direction upward, this one will be a downward. Okay, so that is about a field, magnetic field line. And electric field lines means what? Terminating from the positive, emanating from the positive and terminating at the negative here. Okay, that is for the a electric field distribution. Now the mode of the propagation here through this particular slot line, it's about a again a quasi TEM wave. Okay, so just like we say earlier for this microstrip lines and all. So okay, that's about a propagation mode propagation through this given line there. Now for the given particular slot, these are the field distributions. So then a characteristic impedance of the given line, because here we say that this line is used to propagate the cos TM wave, okay, through this particular line. So that's why a characteristic impedance, if we define for the non-TM wave, it will be difficult then. So then how to identify the or how to calculate or how to obtain the characteristic impedance of the line? So characteristic impedance of the line, if it is a non-TM wave, then it is to be obtained through the what will be the power and a voltage relationship through this particular line there. So we can write a characteristic impedance of a given line here. So ZO is equal to characteristic impedance of a transmission line is equal to what will be the voltage we apply divided by price of power P here. And that P is nothing but what? A peak power or a uh, peak that sorry, you know, average power. V is nothing but what? A peak voltage. Okay. And P is nothing but what? We can say that a average power. Okay, so that is about the peak voltage. That peak voltage is available across the given particular slot. Okay, this one. And then this one is about the average power. So means we can find out the characteristic impedance of a slot line based on the voltage and a power there. But in the case here, that peak voltage appears across the slot, it is depending upon that what would be the width of the slot here. So that's why we calculate the characteristic impedance of a slot line, that is depending upon the width of the slot. If we say that the slot width is increases, okay, this one we can say that that slot width will be increases, that is about a W, then the characteristic impedance will be increases there. So that's why based on this difference between this width here, okay, that W, that slot difference, if it is increases, characteristic impedance increases, then again your frequency will be increases here, or frequency will be very rapidly if we supposed to consider that increasing the slot there. If you compare with a microstrip line, with this particular microstrip line means what? We have a given line. This one is about a ground plane here. This means this is ground plane, and this one is about a strip. Okay, so that is about a small strip. That is about a microstrip line. So in that particular case, we say that for a given microstrip line, frequency is depending upon that width, thickness, and height. But here the frequency is depending upon that what will be the separation between the two particular slots there. And the losses, if you compare, what will be the losses? Again, we need to talk about that. What will be the effective substrate value? Okay, that's about epsilon r. And we have seen earlier that effective substrate value is equal to what? A epsilon r plus 1 by 2. And this one is about the effective substrate value for the a slot line. And then a losses, if you talk about the losses here in a particular line, losses are due to what? A dielectric losses. We see that lossy dielectric or whatever the material we are using. As well as a losses are due to what? We are using here a conductor. That's why we can say that a loss is due to the conductor one. Okay, whatever the conducting material we are using. So we have the losses due to the a conductor there. So now these are about the losses. Losses due to the dielectric as well as the losses due to the conductor. Because whatever the substrate we are using, okay, if it is a perfect, then losses, dielectric losses will be zero. But substrate are not perfect, so imperfect dielectrics, or we can say that a loss is substrate. Then in that case, there will be a dielectric loss. And due to these dielectric losses, we get the a propagation constant value, that is gamma, that will be a complex. And the dielectric loss of this particular substrate or this particular slot line can be obtained through the loss tangent value. Okay, that is about a tan delta. That is about a skin depth. Okay, so this way we can calculate the a losses in the slot, dielectric loss. Then what about the conducting losses? Conducting losses are nothing but what? Whatever the strips we are using. Okay, so then in that case, what will be the surface current distributions on this particular that plot, that is about a conducting plot, and based on that we need to find out what will be the dissipation, energy dissipation on this particular surface. Then that energy dissipation through the surface, because the surface is a conducting surface, so that's why it has some surface resistance rs. So that's why a conducting loss is depending upon that a surface resistance of this conducting strip line here. Okay, conducting strip. So that's all about what we can say a slot line. Now next we see here, okay, another line is about, we we say that earlier a micro strip line. So now if we consider that a strip line, okay, generally word we say that a strip line. So from the strip line, they have the configuration of what? A micro strip line. It has the configuration of what? A coplanar line. Okay. It has the configuration of a slot line. Okay. So now these are the but how this strip line looks like? Okay, so we have seen that various configuration of a micro strip there, but a strip line means what? If you consider that strip line is what? It is about a metallic conducting metallic patch. Okay, we just see the a cross section view of a strip line. So now in this case, what happened? This one is about a conductor. Okay, these are about a conductor. Okay, that is in a strip line. So now these are the conductor there, and in between that there is a small strip. Means if we consider that a strip line, so strip line it has a three conductor. Two are a ground planes. These two conductors to be a ground plane here, and one is about a main conductor here. In a macro strip, it has a two conductor. In a coplanar line, it has a three conductor. In a slot line, it has a two conductor. Okay, so likewise. So we have the again another configuration is about a parallel line. Okay, what you can say that a parallel strip line. Now this configuration is about a what you can say that a strip line configuration. This one is about a strip line configuration. In a strip line configuration, a small strip is there. It is present in between this in between these two conducting plate or a two ground plate, and that ground and this strip is surrounded by a dielectric material. Strip is surrounded by the dielectric material or a substrate. It has a value epsilon r. Then for a given particular strip, if you consider that what will be the thickness of the strip and what will be the width of the particular thing, that particular strip, according to that a characteristic impedance will be calculated. Okay, so now we see here what is the thickness. So this one is the body thickness. Okay, that is about a t. Now this one is about thickness and this one is about what we can say that width. Okay, for this given particular strip, this one is about a width. Okay, and this one is about a thickness here. We stay here. This one is about what you can say that a thickness, that is about a t for the a conductor. This one is about a conductor. So if you see the field distribution for a given particular strip line, so in that case here we have the plane. Okay, a ground plane we say, and in between that we have a strip. Okay, so this I just use one. This one we have a strip now. Okay, so now we can say that this one is about a strip conductor. Then this line, okay, that is about a we have this structure here. So in that case, your electric field and a magnetic field. So around this conductor there will be a magnetic. Around this strip there will be a magnetic field. But for the electric field, because this one is about a positive now, and this one is nothing but these plates are act as a ground. So in that case, so this one is about what we can say that a electric field component of the this one about a strip line, because field emanates from the positive and terminate at the negative. Now this one is about a electric field component. So field distribution. These are about the this one we can say that a E now. Okay, this one is about what we can say that E field, and this one is about a H field. That is about a magnetic field. So electric field and a magnetic field. Now here, if you consider that this particular line here, it has a three layers. Okay, it has a three layers. One is about what we can say that a conductor. Okay, this one is about the inner conductor, that, or we can say that this one is about the main conductor, and other two conductors are nothing but a ground conductor. Okay, these are about nothing but a ground, and in between that this conductor, main conductor and a ground conductor here, there will be a substrate that's about a epsilon r. Okay, that we can say that a substrate. So in the case of a, we can say that a microstrip line, that strip is on the substrate. Okay, strip is deposited on the substrate. Okay, or means on the one side of the substrate there is a microstrip line. Okay, small strip, and another end of the substrate there will be a ground plane. But here substrate, both the end of the substrate there will be a ground plane. But in between that substrate there will be a conductor, or you can say that's about a strip here. Okay, so that is about a strip line structure. Then next about a parallel strip now. Okay, now we talk about a parallel strip. So in the case of a parallel strip line, what happened here? So this one we supposed to consider this one a parallel strip line now. Okay, so parallel strip line, in a parallel strip line, so it has a two conducting wire. These are the two conducting slabs, or we can say that a two conductors. These are a parallel one, and in between that it has a substrate. This one is about a dielectric substrate. Okay, now these are the two metallic strips. Okay, these are nothing but a two metallic strips, and these two metallic strips are a parallel. Okay, these two metallic strips are a parallel, and in between that there will be a, that is about a substrate that's called as a, what you can say, that value of a substrate there, and that is nothing but a structures of a parallel strip line. Then one of the line will be positive, then we can find out easily directly what will be the field there. Okay, so that is about a parallel. So around that, so one is the positive, so field distribution. Okay, field distribution, electric field distribution emanating from this and terminate here. So around that there will be a magnetic field here. Okay, for the given particular line. That's all about what we have learned that. Okay, yesterday we have started a microstrip line, and we have seen that. Okay, that's about a microstrip line, their configuration, their field distribution that we have seen yesterday here. Okay, so now uh, we have seen today that is about a strip line. Okay, so then we have seen today that is about a parallel strip line. Okay, so these are about the, and we have seen that a slot line. Okay, that's about that's all about what we can say, that a micro strip line and their line configurations there. Okay, strip line, or we can say that this particular topic belongs to the a planar transmission line. So now each and every we can say that strip, so they are characterized based on the character impedance and a propagation constant. And all the factors, character impedance and a propagation constant, that are depending upon that what will be the size of a conducting strip, and what will be the width or thickness of the conducting strip there. So that's all about what we can say a strip line here, and so we stop here for we learn strip line. Thank you.